Good morning, everybody. So as Dr. Letcher said, we are the laser engraving and cutting group. My name is Mark Laskin.
I'm Alexander Auk.
Jacob Weisbro.
I'm Wyatt Fierce.
And our sponsor for this project is Trigger Interactive. Sorry, my apologies. Havoc Interactive.
Just a quick little background on our sponsor, Tyler Rockwell and Havoc Engineering. He currently has a 30-watt CO2 laser engraver system and uses it for his various businesses. His wife has a business, Birch Design Company. He's a mechanical engineering alumni and is currently looking to upgrade his laser.
So getting a little bit into the introduction here. So the current solution that Havoc has is he's using a 30-watt laser for his business, and it's effective in engraving, but not really in the cutting aspect, and that's really what he wants to get into. So with us, we're going to provide him basically a 100-watt laser, CO2 laser, which will be able to provide still that engraving quality that he's looking for, but is also that cutting different types of materials, especially up to about a half-inch piece of plywood, which is really big for what he wants to do. The other big reason why he's going to go through a scene design program like us is because it's really going to allow him to build a really inexpensive build. Looking at it, and we'll get into it later, you know, with a budget of about $4,000 when he came in, and still being able to be about $5,000 is way under what the industry market is right now. A typical 100-watt CO2 laser from just a corporate business that you can find is about $40,000 to $70,000, which is really expensive work. We can be well under that. It's going to save him a lot of money in the long run. And the other thing that we also are going to do for him is, in the process of laser engraving, and we'll kind of show this a little bit later, is to properly do it. This laser itself is going to be stationary, and we have a separate Z-axis table that will move the parts up and down to be the appropriate distance. Currently, it's not a great system that he's using. It's just a hydraulic pump. If you think of a barber's chair where he's just pressing a lever and it goes up and down, what we're going to do is ideally give him an automated system, which will just make it a lot more accurate and a lot easier on him.
So some of our main goals that we're looking at is making the actual laser bed cutting size around 2 foot by 3 foot. There's a metric conversion, but it's pretty close to that. We really want to get that 100-watt just because it's the happy medium of what we can cut versus what's too expensive, and size constraints as well, because those laser tubes are pretty long. I think this one's about 4.5 feet long to get that 100-watt. The next thing is we want a red dot laser diode that runs along the same gantry system as the cutting laser, and you can use it to mark out and guide what you're going to cut. And it's a neat little feature to have, especially for a lower end system. We want LEDs inside of the enclosure to make sure that everything can be seen. Our sponsor's current system is pretty dark on the inside once you close the tinted glass, so it can be easy to miss if there's obstruction or something that's going to interfere with the laser running, and that's one of his biggest frustrations, so we want to make sure we cover that. And then we have to make sure that everything's properly ventilated, and our sponsor specifically requested that we use as many off-the-shelf parts as possible so that if something breaks long-term, he can replace them easily. Some of the things we might have to put us to more of a stretch goal, but we think we'll be able to cover them, is that automatic Z-axis table, and then potentially a sensor that will automatically adjust for that Z-axis to make sure that it all fits perfectly the first time. Some of the things that we're not going to be able to do is a pass-through slot, which is a system where it takes the entire cutting table and it can pull it out of the laser so that you can reapply a material or place a new material on it and then moves it back in. You see it a lot with solid laser sintering systems, but we're not going to do any additive manufacturing with this, so we won't need that. And that pass-through slot and auto loading systems are pretty integrated, so we're not going to use either of them. It's just outside of the budget we have, and we shouldn't need to cut anything bigger than 3 feet. So that's pretty much where we're going to stay with that.
Okay, so for one of our first in-class presentations, we did a review over the state of the art of both laser technology and CNC technology. In this, we found that all types of lasers contain the same 3 main components. Those 3 main components are the resonator, the pump, and the gain medium. The gain medium is the most important component of the laser. as it determines what type of laser you're working with. As in this example of a carbon dioxide laser tube, the carbon dioxide gas mixture within the laser is the gain medium. And this contains what are called dopant ions that emit the electromagnetic radiation in the form of the laser after they decay. Gain mediums can be gas, solid, liquid, gas, or gaseous, and overall they determine the electromagnetic wavelength, bandwidth, overall beam quality, and the power of the laser. The second component is called the pump, and the pump is any device that excites the ions or dopant ions within the laser tube. This can exist as a flash tube, or in this example, it's a power supply that provides an electric current through the tube, or it also could be another laser called a semiconductor laser diode. The third component is the resonator, and the resonator is just two optical mirrors on either end of the tube that reflect the beam back and forth within the tube, and this itself provides positive feedback and amplifies the beam propagation within the tube.
All right, so we wanted to look at some laser types just to make sure that we were buying the correct laser. So we looked at 3 different laser types: a CO2 laser, a YAG laser, and a fiber laser. It was pretty clear right away that price was going to affect us. I mean, the YAG laser and the fiber laser are both $2,500 to $5,000, and that's a lot more than you can get for a CO2 laser, which could potentially run long.
So piggybacking off that, since we decided we're going to go with CO2, we also want to just evaluate those different levels of CO2. Basically what that is just the overall power wattage that the lasers provide. These can range from anywhere from, again, 30 watts to 15,000 watts if you get really the big industrial laser engraving and cutting. But for our purposes, we kind of looked at that sweet range of about 90 to about 120. Because if we go over that, we start getting into poor quality engraving, and as Alex said earlier, just kind of out of the scope of what we need for this project specifically. So evaluating all those different types of lasers, we kind of came down to that 100 watt just being that just ideal engraving and still being able to cut through, again, about a ½ inch of piece of plywood, as well as some other materials like plastics and
One of the big things that we're looking at adding is a chiller system rather than just a water pump system to maintain the temperature of the laser tube. This should allow us to stretch out the lifespan of our laser tube since it won't be overheating and the CO2 will be more inert. It should last longer and should perform better for many years to come. So we wanted to look at which chiller system is going to be the best. And we started by looking at the OmniTech and the MCW. And they're specifically laser engraver chillers. They're the best equipped. It is a more universal chiller, but they all work the same system. It's just marketed to more broad systems, so it's a little bit more cost effective. So being just as efficient and more cost effective and just as applicable, that's the one that we decided to go with.
Right, so to come up with a solution, a viable solution for Tyler or Mr. Brockle's hydraulic lift table, we needed to perform some torque calculations to determine what type of motor, the size of motor, and how many motors we might need for the table. To do this, we had to abide by some weight requirements. Those are that we need to lift the laser bed and exhaust bin assembly we designed. This will be constructed from aluminum, so it should weigh around 20 pounds. And some of the common engraving items that Mr. Brockle currently uses, like this ammo can, they weigh between 6 to 8 pounds. But with this project, he would like to lift and lower some heavier items using this automatic Z-axis table, and those can weigh between 30 to 35 pounds. So with using the load raising and load lowering torque equations, along with some specifications with these lead screws, which Wiley will talk about, we can find the required torque for this table.
Okay, here's some numbers for the torque load raising and load lowering equations. As you guys can see, the load raising equation only required 0.389 foot-pounds of torque for the 30-pound load, and our 60-pound load required 0.777 foot-pounds of torque, and our NEMA motor provided 0.929 foot-pounds of torque. So it's looking like lifting 30-pound loads should be fairly easy.
So our sponsor also asked us to look at basically just a bed box. Since lasers, obviously cutting materials like wood and other things that will cause soot, smoke, and just other particles that you really don't want to breathe in and just in your air in general. We have to vent those out properly. So since the laser is going to be cutting down, what we do is we have the honeycomb bed, which is what everything's going to sit on, which allows the particles and materials to fall through into this vent box, which can then be vented out separately from the system. To do this, currently our sponsor has a fan that is capable of going up to 402 CFM, which in current manufacturing in the industry of CO2 lasers, for 100 watt, that's kind of the range that they're looking at, is anywhere from 400 to 600 CFM, just to make sure we're giving enough CFM power, which will just basically suck out that unwanted particles and material. We're also going to potentially put just a cheap computer fan on the back of the vent box itself, and that's just going to provide an additional about 110 CFM, which will really, again, make sure we're sucking out enough material and so we're not contaminating the air we're trying to breathe, as well as other issues that we might have.
So getting into our design pieces, the first thing that we really intrinsically designed is the laser enclosure assembly. This is the actual framework that's going to go around the gantry system, the laser and the control components for it. And it is specifically meant to protect those components, keep them safe, but also protect the user from any stray laser reflections, and just make sure that they are safe and protecting your parts while it's engraving. So for the most part, it's going to be aluminum extrusions with faced aluminum plating, and then a tinted rose tint plexiglass for the actual laser bed area in the middle. And then off to the right side is where your control components are going to be, your stepper motors, controller boards, all of that. And then in the back compartment is where your laser tube and then how the hoses for your chiller are going to run through there.
Okay, so here's our current design for our laser base or laser frame. This would just be a table that the laser enclosure could sit on top of. And we've allotted some extra space for that chiller, which would sit outside of the laser enclosure. And then the adjustable Z-axis table we'll design should fit underneath on the cutout on the left. This assembly is made from the same extrusions, aluminum extrusions, as we use for the other assemblies. And the tabletop is an 1/8-inch thick aluminum sheet. Each four of the legs have a lockable caster, so it's easier for Mr. Bockel to transport. And then, we just have some extra braces in here for some rigidity. And overall, this table should be about 41.5 inches tall.
Okay, now going into our design solution for our Z-axis assembly. It's run by the Nina 22 motor, like I said before. It's belt driven with 4 lead screws, and again, it's made out of the aluminum extrusion. The exhaust port. We've got special retractable casters to ensure the leveling of the bed frame or the laser bed to the level, so it's level with the laser itself.
And again, just looking at our Gantt chart, which is basically kind of our next steps for the project. We've kind of just started, again, next steps, really big steps, are going to be finalizing those designs so we can start getting things ordered for the upcoming spring semester so we can start doing these assemblies. We also have our CDR presentation, which is just the last presentation we'll do with our design review committee members, just to, again, finalize these designs and applications that we want to do to make sure, again, we're providing the best product to our sponsor. And with that, again, we're going to start ordering parts. Once we get those parts ordered, we'll start doing the assemblies, hopefully as soon as winter break here, and then get into a couple different reviews over the semester, and then eventually the expo come April.
Currently, where we're sitting on our budget breakdown, we just ordered our parts. They just came in on Friday, so that came in to be about $2,000. Unfortunately, shipping prices are going way up right now, so that kind of made us tighten up our belt a little bit. And our chiller's priced out, and we got that ordered as well. Our assembly is a rough estimate off of what the parts are looking like from McMaster. And then our base assembly and our Z-axis table are about what we have budgeted left. So we're right around that 4,000, a little over mark at the moment. So we're, for being, 10% of what a normal company would charge you for a full laser system like this, we're doing pretty well so far, but we gotta be careful to make sure that nothing extraneous comes up, or else it's gonna get expensive fast. But that's just the nature of working with this type of electronics.
So again, as the last group stated, we have the QR code that you can scan, or feel free to go to the link. And if you can't do either of those, we do have paper copies for you guys to review our presentation. And at this time, we will take any questions. Yes.
So you said that you're making like a 40-inch tall cart, and then your design cutter itself is another 40 inches. So that's like putting it at over 80 inches tall, so that's 7 feet in the air.
It's all gonna get chopped down.
Yeah. So
Especially
The cutter isn't that tall.
So it's taller than what we had. It's
Yeah.
shorter.
It's shorter, yeah. It's overbuilt for the purpose of that model, but even that model isn't 40 inches tall. So.
So you're looking at using lead screws, right, to raise and lower the bed.
yep. So
So are you looking at, have you ever thought about using like a worm screw so it's not gonna back, like maybe, I don't know, twist itself out or lower when you don't want it to or anything like that? Or will the system be able to hold that much weight in place?
it should be able to hold most of the weight in place. Worst come to worst, again, we really try to prioritize just one lead screw because kind of with that question, we did consider if the system slips. If you have more than one lead screw, basically, if one of those lead screws slip and you're on a separate motor, you have to do, basically hand adjust it to then meet up with that other motor. So ideally with one motor, if the system's going to slip, it's going to slip altogether. However, from those torque calculations, the motor should be strong enough where it should hold everything in place properly. But to your point, that is a good thing to consider. With that, we also, a little off tangent here, but we also did try to consider doing another hydraulic system for him, but that's automated. Just because with hydraulics, you are basically guaranteeing that pressure is going to stabilize it perfectly. However, hydraulics are very expensive, especially just for the system that we need, where lead screws were just the most effective, just cost-wise, and would still work to hold up properly.
How are you gonna secure the part that you're cutting and engraving table?
So for the most part, you don't secure those pieces. They just sit and they rest on that laser bed. If you really need to secure that piece, most likely you're not in a stable enough solution to be using a laser cutter. This is all factory setting, everything just resting on there. If you have an off-centered piece that you actually need to block up, you would create a fixture that it sits on to hold it square. But for the most part, there isn't really a need to secure whatever you're laser engraving to the bed, because when that laser is actually hitting it and running over it, it's not shaking the part, it's not moving the part. It's not like when you go mill something and you can hear it chattering and you don't have it braced in tight enough. When you're lasering it, it's literally just light moving over it, and any part that it's actually hitting is getting sublimated away. So it doesn't move the part at all.
And to piggyback off that a little bit, the Z-axis table is what the parts will sit on, which is separate from what the laser is going to sit on. So it's two separate tables. So even if the laser, when the gantry system is moving, was to just shift it slightly, since it's a separate table, it shouldn't affect the part itself.
Why did you guys go with moving the table rather than?
The fact that you have to work at the laser height, so putting the laser at a set table and then moving the parts to it is a lot easier and gives you a lot more opportunities than if you were to move the laser height, because you have to work with all the controls on the laser. And if you're working on something that's tall and you're working up here on your control systems, it's really irritating, as well as if you're working really low. So you want your laser to be at its set height that you're just going to work with, and then you can vary the parts that you move in and out underneath it. It's more convenient and it's less moving parts. Also, that laser tube is not cheap and it's very, very delicate. So you don't really want to be moving it too much. You want that to be as stagnant and stationary as possible, just in the event that something would happen where it could get shook loose from its housing and break. Because then you're out half the budget of your laser.
And with that, I think we're out of time, so we would like to thank everybody for coming today and taking time to listen to our presentation.